Hello! Today I'm going to charge, discharge and then charge again this sodium ion battery, and using the graphing facility of this DL24EW electronic DC load, we're going to take a look at the charge and discharge curves for one of these HAKADI 1500 milliamp hour sodium ion batteries. Here are the specs from the AliExpress listing for this sodium ion battery. We're going to charge it to 4.1 volts, then discharge to 1.5 volts. Now the maximum charge current is 1C. I'm going to go a little bit below that. C is 1.5 amps, 1.5 amp hours. So I'm going to charge it at 1 amp. That's the 1.0 up there. Then I'm going to discharge it. The maximum discharge current is 3C, but I'm going to do it at 1C. So I'm going to discharge it at 1.5 amps down to 1.5 volts. Okay, let's get started. Let's switch on the charger. Now set that to 4.2 volts, even though this discharger is set to stop charging. In other words, it'll turn off this charging module at 4.1 volts. The reason I've put this to 4.2 is so that we get the constant current charge, but then the current will drop off slightly as the voltage gets very close to 4.1 volts here, and so that we just get a little bit of saturation in the charge. Okay, let's start the charge and then I'll talk you through some of the numbers on this display. So up here, top left, you can see that the current being pulled by the charger. This is just a switch, it's just a MOSFET. So the constant current is done on your battery charger. That's being put into the battery. So let's get in a little bit closer on this display. This is the charging current that's being measured. So it's very close to 1 amp. The battery is currently at 3.86 volts. So the voltage, which is the yellow line, will creep up. Now this graph starts full screen, and then gradually as the data accumulates it squashes down so that it always all fits on the screen, but the scale in minutes, which is this purple, these purple numbers here, will squash down so that we can always see the entire graph. Now you won't get a full charging graph because I'm starting at quite a high voltage, but what we will get is a full discharging curve. Let's just go through a few of the things on here. So I'm doing a CDC program, which means charge, discharge, and then charge back up again. IS is the discharge current, so that will be at 1.5 amps. There's no overprotection set on here. The stop points are when it discharges down to 1.5 volts. In terms of charging, it will change direction when it gets up to 4.1 volts. There are limits set at 150 watts. We're never going to get to that. And also 100 degrees C. Well, I don't even have the temperature sensor fitted. So currently this is the voltage curve. You can see the actual voltage right now, which is 3.93 volts. This is the measured current coming in from the current limited power supply, and that's also shown here with the purple line, which you can see is at 1 amp. Now this display is a bit strange. The very last square runs in real time with 1 pixel per second, so it's about 15 seconds. All the squares up to the last square show the entire charge and discharge curve, and as I say, the scale will gradually close up, but the last square is always a 15-second interval, so there will come a point where the last square will look a bit strange. The cell is now at 4 volts, still charging at 1 amp, and we're going to 4.1 volts, whereupon this charger discharger will change direction and start discharging at 1.5 amps. There are counters down here for amp hours. So in the discharge curve, we'll get a total amp hours count. And this cell is 1500 milliamp hours. So we should see 1.5 amp hours. There's also a watt hours count. This is total elapsed time, probably for this phase or stage. So this is stage 1, of CDC, which is charge, discharge, charge. Stage 1, of course, is the charge stage, now up to 4.05 volts. And now the charger power supply is switching over from constant current of 1 amp to constant voltage at 4.2 volts. That's what I set it to. So we'll start to see the current that the battery is being charged at fall away once it goes into constant voltage permanently, which it's just done. So that current is now falling down. And you can see here over on the right hand side, the current is falling away, but the voltage hasn't yet got to 4.1 volts. It's 4.09. It's the power supply charging this thing is at 4.2 volts, but of course there's a bit of voltage lost in the wire from my charger power supply into the charge module of this electronic DC load. We're just hitting 4.1 volts now. This should go into phase 2 or stage 2 fairly soon, which is the discharge stage. And it will be interesting to see what happens to the voltage of the cell, how quickly it pulls down once it starts discharging at 1.5 amps, which I believe that's just happened now. So this is now in stage 2. The voltage of the cell has fallen away a little bit. We can see that here, 3.94 volts. So it holds up reasonably well, but not at 4.1 volts. It quite quickly falls down to 4 volts. So you could argue that the space between 4 volts and 4.1 volts is fairly small area under the curve, because the rate at which it falls down is very sharp. Phase 2, the discharge phase, should run for an hour because it's a 1.5 amp hour cell and I'm discharging at 1.5 amps. So what we want to see here is 1.5 amp hours, and on the timer we want to see that the discharge curve lasts for approximately 60 minutes. And you can now see that the charge power supply, the constant current power supply, has gone to 0 current because it's not now being used. It's still switched on, but the switch unit here, which this device uses to charge the battery under test, has now been disabled, and the battery is being discharged into the heat sinks under this fan, and if they get hot enough, this fan might come on. Now this electronic DC load is Wi-Fi. It's also Toya or Smart Life compatible, so there is an app which I'm running on my phone. And this display of course can't show everything, particularly in graphing mode, because there just isn't enough space. So here you can see a few extra bits and pieces. We can see that the mode is in, well, bizarrely, DP Fun Set DCD. They got that the wrong way around. It's supposed to be CDC, charge, discharge, charge. So it's there are a few anomalies in this app. But one thing I wanted to show on here, which you can't see on this display, is that the fan temperature, or the board temperature underneath here, is currently at 33.5 degrees. If that gets up to, where is it? Yes, if it gets up to 42 degrees, then the fan will come on. So what can we see from this graph so far? Well, we charged to 4.1 volts. Then it immediately switches without a gap to discharging at 1.5 amps, and you can see that the voltage fell very quickly to below 4 volts. It's not easy to see that, but because of the scale of this graph. Now, I have charged this a couple of times prior to this video, and I charged it to 4.1 volts and then had it with no discharge load, and it held up pretty well. It fell fairly quickly to about 4.05 volts. So certainly the cell doesn't immediately fall away from the 4.1 volts that quickly. It's quite happy to sit up there at above 4 volts, and it took quite a while for it to drop below 4 volts of its own accord. So just looking at the way it draws this graph, It's 1 pixel per second in this last square, and you can see it counting up to the end. Then it redraws the entire graph, rescaling all of this previous stuff, and then it does another 15-second count, or it might be 16 seconds. I think it's probably 15 because it's a quarter of a minute, to fill in this last bit. So the graph looks a bit peculiar because the scale of all of the first whatever number squares that is, bar the last one, is this scale where 18.4 minutes is up to this last line. But then this last square only shows you the very latest 15 seconds. And when we start seeing the curve coming down at quite an angle, once this is all squashed in, you'll see that the curve looks very peculiar because it'll be curved up to this point and then it'll be a flat line in this last square. It is a bit odd. So voltages in yellow, this is the voltage scale. Current when you're discharging is in green, and all of the discharge parameters, amp hours, watt hours, total elapsed time is in green for phase 2, which is of course the discharge phase, the D in CDC. When it's charging, the current curve is purple. So we can see that when it was charging, it was 1 amp, apart from that very last section where the current fell away a little bit while the battery got up to 4.1 volts. And then, of course, it switched to this higher current of 1.5 amps for the discharge phase. You'll notice that I've just pushed on these Vruzend cap covers in order to give me a connection to the cell. I just thought it would be the quickest way to do it, but they were extremely tight and I could really barely get them on. In fact, I think the only reason I actually managed to get them on is it's very hot at the moment, and so the plastic of the covers is quite flexible. Now this means that the cell is actually quite a large diameter, so let's measure it, because I think these are substantially over 18 millimeters. So let's have a quick measure of that. Yes, so they're fairly fat at 18.3 millimeters, and length is about right at 65.3 millimeters. So they're a bit over the 18 and, well, a fraction over the 65, but relatively speaking that's much less of an error. The sodium ion cell is now down to 3 volts, still discharging at 1.5 amps. It's been running for 27 minutes. Remember that the upper charge voltage is 4.1 volts and the voltage that we're going to discharge down to is 1.5 volts. So far the curve is more or less linear. There are a few little changes of direction in there. You can see what I mean now about the last square being a totally different time scale to everything else. The first 14 squares, there are 15 in total, are at 35.5 minutes for those 14. The last square is 15 seconds. So you can see that as it's drawing, I don't know why they did this. I think it's so that you get some sense of movement. So you can actually see this square being drawn, but it is a totally different scale to the rest of the graph, which is slightly odd. Yes, so now below 3 volts, we're coming all the way down to 1.5, which is down here somewhere. This graph is linear, of course, and it starts at 0, so you can see the voltage all the way down from about 4 volts at the top there, and 0 is at the bottom, so you can see it. You can get a sense of scale between 4 volts, 3, 2, 1, 0 at the bottom. Now at the 30-minute mark, so theoretically halfway through the discharge, and we've got 750 milliamp hours, so it's looking good for getting the full 1500 milliamp hours that this cell is rated for. So we are watching a sodium ion battery being discharged into an electronic DC load. Now I realize this is very nerdy. For a lot of people this would be like watching paint dry, But I've looked on YouTube and I can't find another video on sodium ion batteries where someone actually has one and they're actually doing something with it. There's lots of sort of theoretical videos about sodium ion batteries and how they're going to change the world of electric vehicles and that sort of thing. But I do believe this might be the first video where a sodium ion battery is actually being discharged and we get to see the discharge curve. I know, super nerdy. Interesting flattening out of the curve here. Like I say, ignore the last square because it's on a different scale, but it was fairly linear coming down here and it's flattened out a bit in the last few moments at about 2.5 volts. Well, I say interesting, it's about as interesting as things get in a battery discharge video, but that was something to point out. So interesting flattening out of the discharge curve. And now after that brief flattening out, which I think lasted for about 8 minutes, it's really started to turn down now. Again, I say ignore the last square because that doesn't show you anything, just movement. Yeah, we can see the voltage has turned down. We're now down to 2.3 volts. 52 minutes. There's only really about 8 or 7 minutes to go, and we're at 1300 milliamp hours, hoping that that will show 1500 or above by the time we get down to, well, this counter will freeze actually when it changes to stage 3, so this will give us the discharge capacity in milliamp hours or amp hours. Now I have actually turned off the charger power supply because I want to see what happens when this discharger, this is just discharging the battery into heat in the heatsink, and that heatsink is now very hot. When the battery is discharged down to 1.5 volts, I want to see how quickly that voltage springs back up again, which will tell you a little bit about how useful the energy in the cell is down at that very low voltage. So it won't immediately start to charge, but only because I've switched off the charger. Now at 1.4 amp hours or 1400 milliamp hours, 56 minutes, we're down under 2 volts, 1.92. I just wanted to check whether this cell's getting warm. Not particularly, but I know that when you take it all the way down to 1.5 volts at 1.5 amps, that very last part does warm this cell up significantly. So the last part of the energy, quite a lot of it is lost in heat as the cell discharges down to its minimum voltage of 1.5 volts. The fall in voltage is now fairly precipitous, down to 1.65 volts. Got a feeling the rate at which that's falling, this is not going to make it to 1.5 amp hours, is it? Because we're rapidly heading down to 1.5 volts, and that's going down really quickly now. I might as well leave the camera running for this last bit. So we're not going to make 1.5 amp hours quite. There's the 1.5 volts. It will now go back into charging mode, but as you saw, I've switched off the charger so that you can see that the current now, this purple line, is 0. And the reason I did that is because I wanted to see how quickly this springs back up from the minimum voltage we took it to, which was 1.5 volts, and it's sprung all the way back up to 2 volts. So we started at 4.1 volts up there. The discharge current kicked in immediately because that's the way this thing works. It charges, discharges and charges with no time gaps. So it dropped immediately to about 4 volts. The discharge was fairly linear until about here, which is about 2.4 volts, something like that. And then it drops away fairly quickly. And although, yes, you can take it down to 1.5 volts, there really isn't much energy under the curve below about 2 volts. And so as a sort of rule of thumb, I think you can think about these cells as having a voltage range roughly between 4 volts and 2 volts, even though the manufacturers say you can go to 4.1 and discharge to 1.5. So that was a full discharge of a 1500 milliamp hour sodium ion battery. There's no lithium in here. Sodium replaces the lithium. And in theory, these should be a lot cheaper in the future because, of course, sodium is massively more abundant than lithium because it's in sea salt. So other than the exotic chemicals that are in here, apart from the other chemicals which I can't find a definitive list of, yeah, no lithium, just sodium. Okay, so let's switch back on the charger. That's now charging at 1 amp, and we'll take a look at the screen and see how the curve starts to shoot up for the final charge cycle. I won't include that in this video because, well, you've suffered enough watching this cell discharge. And now we can see that with a charge current of 1 amp, the cell voltage is pushing up, and this device will now charge it all the way back up to 4.1 volts. So that's it, the first ever discharge video of a sodium ion cell.
Press the like button.
Cheerio.